Good morning, all. I will quickly unmute you so that I know that you can hear me and you are also seeing my slide. So I just need a response from 1 or 2 persons to know that.
Good morning, sir.
We can hear you, sir. We can see your slide, sir.
I hear you, sir.
Okay, we can start. Let me mute you again because some of you, again, for the often times, once you are in an online class like this, you mute that is the first thing you do. You mute both your video and the voice so that you don't distract others. If I want you to answer a question, I would say so, then you can unmute yourself. So good morning. Again, this is CHM 121. I am Dr. Abayomi. I'll be starting because in the course of these course for this semester, you'll be interacting with various lecturers, precisely about 12 lecturers that will be taking different topics. Today, we'll be starting with physical chemistry. In due course, we will also share the course outline so that you know the topics that we are supposed to cover for the semester, and you can do the needful by reading ahead if you wish so and preparing yourself for the class. Again, for this first part of the lecture, that is the physical chemistry one, I'll be teaching that part with Dr. Abdulwahab and Dr. Agunbiade. They will be coming as may require. Same thing with the other lecturers that will be taking the other part of the course. The session is also being live streamed on YouTube. I've posted or sent for the link to both WhatsApp for sharing and also on the chats of this Zoom. So you can quickly scroll back and see so that if you miss any of the discussion, you can go back to the needful. So we'll be starting with chemical bonding, precisely electrovalent and ionic bonding. We know that bonding is one of the fundamentals of chemistry. In fact, chemistry is about interaction of atoms, and these they do by undertaking one type of bonding or the other. We'll be coming across some of these interactions, which we call bonding, as the lecture progresses. But before we go on to the type of bonding, let us first establish some basic knowledge of chemical interaction, chemical bonding, as we might have come across or not. So chemical bonding is the attractive chemical force which keeps the atoms in any compound together. This force is called chemical bond. In other words, what we are saying is that for you to say you have an atom, there must have been some form of interaction between the atoms that you have in that compound before you say you have a compound. So we know that as far as the Dalton atomic theory is concerned, atoms are the simplest entity that can take part in chemical bonding. Okay, so compound arise because of the interaction of these atoms. And as we go on, you come to see that this interaction is facilitated by exchanges of electrons, or interaction between the electrons of one atom and the electron of the other atom that is participating in bonding. So chemical bonding is the phenomenon of chemical substances being held together by attraction of atoms to each other through sharing or by exchanging of electrons by various forces. It could be electrostatic force, it could be some other less pronounced forces. But be that as it may, the key word here is that you have attraction between atoms. And this attraction is facilitated by exchange of electrons between one atom and the other. So to understand chemical bonding, you must know two concepts, what we call the valence electron and the octet rule, or duplet rule in the case of hydrogen. So the valence electron, without wasting time, I know that I can give my shares that you know that the valence electrons are the electrons in the outermost shell of an atom. Again, we say shell because we know that the structure or the physical representation of an atom is such that you have a dense nucleus, which consists of the proton and the neutron. And you also have navigating around this nucleus in a continuous motion are the electrons. Now, the electrons are not just clumped together in one point around this nucleus. They are found in different energy levels, which we call orbiter, or which we can call shell. Okay. Now, the energy of this shell increases outwardly from the nucleus. Okay. That means that electrons are distributed in this shell in different numbers based on the rule that we have come to know as the 2n square rule, where n is the orbital number. So if you have an atom that has 3 orbitals, for example, then if you start counting outward from the nucleus, the third one from the nucleus is the valence electron, the valence shell. And the electrons in those shells are called the valence electrons. So not all electrons in a given atom participate in bonding. Only the valence electrons are available for bonding. In other words, I've just told you that the valence shell is the outermost shell when you count from the nucleus of an atom. The outermost shell, the farthest shell or orbiter, is the valence shell. The electrons you have in this shell or at this energy level are the valence electron. And primarily, these are the electrons that interact with another electron from another atom, okay, and facilitate attraction or chemical bonding between the atom and another atom. So that is why the second point here is emphasizing, that is what is emphasizing, that only valence electrons are available for bonding. That is the electrons in the outermost shell of an atom. For representative and noble gas element, these electrons are always found in the S or P subshell. Now, the S or P subshell, the S and P there should not be strange to you. That gives the various energy level or orbiter or suborbiter of an atom. the S being the simplest and the P, we have the PS, PY, PZ, and so on. So electrons are so distributed in that. I'm sure you must have done a lot of this in FSC 112. So using electron configuration to determine the number of valence electrons. For example, if you have carbon has 6 electrons in total. And if you do your electronic configuration distribution, you know that only 2 electrons can go into the first orbital. The first orbital only contains this S suborbital. The S suborbital can only take 2 electrons at a time. So only 2 electrons will be in the first orbital or shell. And this also follows the 2n square rule, because the first orbital is 1. When you substitute in your 2n squared, it gives you 2 in totality. So 2 electrons can only go there. For the second shell, maximum of 8 electrons is allowable. But for carbon, you have just 4 remaining if you place 2 in the first shell. So that means the other 2 are so distributed as shown. 2s2, 2p6. For oxygen, you have, of course, 1s2, 2s2, 2p4. And for sodium is as shown. You can see that for carbon, those in red, you can see my cursor moving over it. Those in red are the valence electron, and there are 4 in total. The same thing with oxygen here, 4 in total. The same thing with oxygen here, 6 electrons in total in the valence shell. And for sodium, you can see that you have 2 in the first shell, 8 in the second shell. That means the second shell can no longer take in any other extra electron. So the remaining electron out of the 11 electrons of sodium move to the 3rd orbital, which is the 3 orbital. Here in this case, 3s1. And it means that for sodium, there's only 1 electron in its valence shell. For carbon, there are 4 electrons in its valence shell. For oxygen, there are 6 electrons in the valence shell. Using the Lewis symbol to designate the number of valence electrons, we use dots to do this. And again, this you've done in FSC 112, so I won't waste time on it. For carbon that has 4 electrons, you can see the 4 dots spaced as far as possible from one another. You also know that when you are distributing electrons, the Ohm's rule, Auer principle, all kick into place. So about Valence is me, oxygen, you can see the number of electrons. There are 6 of it. If you place 1, 1, 1, 4, then you start pairing. So it means that there are 2 lone pair there. For sodium, just 1 electron in the valence shell. So for the you straight away the number of valence electrons you can have in an atom by that dot representation. You can see for neon, which is a noble gas, it has completely filled outermost shell with 8 electrons. So again, this is your periodic table at a glance to show the electronic configuration of some of those elements indicating their valence electron. Valence electron only. You can see that for aluminum, you have 3 valence electron. For phosphorus, you have 5, and so on. What you can glean straight away, and based on what you've learned also in FSC 112, is that the number of valence electron corresponds to the group of the elements. you can see that for the first group, they all have 111 electron and in their valence shell, and that is why they are so listed. For group 2, they all have 2 electrons, but you notice that the valence shell are different, even though they are all s orbital for the s group element, but they all retain 2 electrons in that valence shell. For the boron group, you can see that they have 3, which is the group 3. The only exception is helium that we place on top of group 8 for other reasons that we don't need to explain here. But the only reason you can think of is that helium has just 1 shell, and the shell is completely filled up. Therefore, helium will behave like the noble gases that have their atom's electron completely filled up. Okay, when you come to the chemistry of the periodic table, that will be taught later in this course to understand why helium is standing here and not immediately after hydrogen in group 2. So this is just a snap view of some of the elements and their valence, indicating their valence electrons. So some atoms have few valence electrons you must have noticed. For example, sodium has just 1. Calcium has 2. Aluminium has 3. So some of these atoms have few electrons in their valence shell, or few valence electrons, while others have more than 5, 6, 7, and even 8 for the noble gases. These atoms like to give up their electron. Now, a little bit of explanation why this is so. The driving force behind every chemical reaction is that the atoms participating in that chemical reaction seek to have a completely filled outermost shell. So take note of that, the driving force, the reason why atoms primarily push themselves to go into chemical reaction or to form union with another atom is for that atom to have a completely filled outermost shell. Now, the way they now do this will determine the pathway of the bonding they use. For example, take sodium. Sodium has just 1 electron in its outermost shell. But in order for sodium to have at least 8 in that third shell, which is also permissible, it will need 7 more electrons. That is one choice it has. Another choice it has is that, look, who will give me 7 electrons? If I can't get 7 electrons, let me shed this one that I have, so that when it shed that one, that third shell is gone. It will be left with just 2 more shells. The second one that has 8 electrons will not suffice. So it means that it has satisfied the ambition of having a completely filled outermost shell. But the 1 electron that it has given off will not just disappear. It is giving it off so that it can form a union with another atom, so that it can have that fulfillment of having 8 electrons in its outermost shell. So the same thing with atoms or elements with fewer electrons in the outermost shell, like magnesium, like potassium, like calcium, like most metals, because most metals have few electrons in the outermost shell. So they prefer to give off this electron, because giving off electron and attracting electron require energy. The more electron you are giving off or attracting, the higher the energy that is exchanged with the environment. Therefore, the environment might not be sustainable. For example, sodium cannot go via the route of gaining 7 electrons, because this will require a substantial amount of energy. Therefore, it goes easy on the one that is easy for it, which is giving up 1 electron. So it gives off the electron. These atoms like to give off the electron, just as indicated, like sodium. And giving off this electron, it is left with 8 electrons in that atmosphere. Some atoms are really close to having a full shell, like fluorine, for example, like oxygen. Oxygen has 6. Fluorine has 7. In either of these cases, oxygen needs just 2. Fluorine needs just 1. So if given the choice of giving off or accepting electron, it is easier for them to accept electron than to give off their 6 or 7 electrons. Okay, so for ease of interaction, some elements, we find it easier to attract than to give off electron. These are atoms with more electron in the atomos shell, like the group 6 and group 7, the atoms of group 6 and group 7 elements. We prefer to accept or attract electron, or find it easy to attract electron than to give off the majority of electron that they have in the valence shell. So, important facts about valence electron. Representative element of S and P subshell in the same group of the periodic table have the same number of valence electron. The number of valence electron for representative element is the same as the group number in the periodic table, which I just explained a while ago, that the number of valence electron more or less correspond to the group number. Group 1 has elements with 1 electron in their valence shell. Group 2 has elements with 2 electrons in their atoms, in the valence shell of the atom, and so on. The maximum number of valence electrons for any given element is 8 for your level. Okay? The maximum number of valence electrons for any given element is 8. That is mostly for the S and P block elements. But if you go beyond this, you will find elements that are exception to this rule. You don't need to bother yourself for now with regard to this. So, octet rule. Octet rule, as it implies, or the name implies, octet. You know that anything that is oct is most likely 8 or 8 inclined. This more or less is saying that electrons arranged with 8 valence electrons are more stable than all others. And that is what most elements of that you come across at this stage of the course we strive to do. They will strive to have 8 electrons in their valence shell. How they now do this determine, is based on the sort of chemical interaction or chemical bonding that they undertake. The valence electron configuration of the noble gases are considered the most stable. Just like you being told that the maximum point or grade point you can achieve in class or during the course of your study is 5, and you achieve the 5, is more or less your content. But if you are still on grade level 1, 2, 3, CGPA of those points, you will strive to work harder so that you can get to the maximum level. For the noble gases, which are the group 8 elements, they have valence electron of mostly 8 in their valence shell. And that is why they are not as reactive as the others. They are unreactive. They are not bothered because they've already achieved what every other atom wants to achieve. They already have 8 electrons in the atom shell. Therefore, they are not bothered. They are just not as reactive. It's not as if they don't form compound or are not present in some compound, but the chemistry of this reaction is different from the usual simpler bonding type that will be coming across. So all noble gases have the atomos and atomo S and P subshell completely filled up. So the noble gases are the most unreactive of all elements. Atoms of many elements tend to acquire the 8 valence electron configuration through chemical bonding. This I have said a while ago, that the driving force for an element to participate in bonding via its atom is for it to acquire that 8 electron in its valence shell. It can do this in different ways, which will be coming across very soon. Atoms of elements tend to gain, so it can do this by either gaining, losing, or sharing electrons to produce a noble gas electron configuration. So there are 3 ways of doing this. Is that the atom of that element gives us its electron, like we've just informed ourselves for the metals. They're giving it up because they just have few electrons in the atomos shell and say, okay, I can do away with this and still survive by combining with another element. So they give that electron away to primarily to the atom that they want to combine with, because there must be a need on both sides. The one that is giving off its electron away want to form a stable valence electronic configuration. The one that is trying to bind with it is in need of electron for it to form. It's just like a buyer and seller. I have what you need, you have what I want, and we can both share. So they can either gain or lose or share electron to produce this noble gas electronic configuration. This results in the formation of compounds because by that interaction, there's an understanding, and that understanding leads to the coming together of the 2 atoms to form bonding. This is known as the octet rule. Now, the octet rule, again, is not the alpha and all of all chemical bonding. There are atoms that are exception to the octet rule. Exception in the sense that even after bonding, they might have fewer electrons in their valence shell, or even have more electrons in their valence shell than 8. But just know that for now, let us establish the foundation for you that the driving force of all elements when using their atoms to bond with other atoms is to achieve or satisfy the octet rule. So when the elements form compound, they do by either losing, gaining, or sharing. I just explained that. So as to achieve the stable electron configuration similar to the next higher or lower noble gas in the periodic table. This idea formed the basis of the electronic theory of bonding. Formed the basis for the electronic theory of bonding. Now, if you have a neutral atom A neutral atom is an atom that has no charge. If I say sodium, Na, that is a neutral atom. But if I say sodium plus, that is no more a neutral atom. If I say fluorine, F, that is a neutral atom. But if I say F negative or minus 1, that is no more a neutral atom. So the neutral atom of an element is without a charge. So laws of electron by atoms. Atoms are the first 3 elements in a period, precisely group 1, 2, and 3. Lose electron from the atom's shell to form positively charged ions. And the few examples as listed below. For example, sodium, we've come across that before, has an electronic distribution of 281. 2 in the first shell that is closest to the nucleus, 8 in the next one, and 1 in the valence shell or orbital. So in order for sodium to participate in bonding, it either needs 7 or it can do away with this one that is in its atomos shell and will become sodium plus. And the electronic configuration of that sodium plus is 2,8. It means that sodium has now ingeniously achieved that ambition of obeying the octet rule, which means that its valence shell or orbital is now 8 and satisfy the octet rule. The same thing goes for the other one. You can see that sodium plus here now. Why do we say, I'm going to unmute yourself and just listen to some of you to tell me why this is just sodium plus, this is sodium 2 plus, sodium 3 plus. Let's hear you for 2 minutes. Okay, if you want to talk, you can unmute yourself. Just tell me your name and department. The question again is why is it sodium plus? Why am I not putting sodium 2 plus or sodium 3 plus?
Good morning, sir.
Good morning.
Like this, because sodium only gives out one electron, one of its valence electron. It only has 1 electron on its last shell, sir.
Okay, why not? Why, if it is giving out electron is negatively charged. Why am I not saying it is sodium minus or sodium 1 minus? Why?
Because
Good morning, sir.
ionization energy is like endothermic.
No, we are talking about charges now. We are not talking
Good
about
morning, sir.
energy. Good morning.
Yeah, this is Victory from Radio Graphic. Okay, the reason why it takes a positive sign is because the amount of protons exceeds the amount of electrons.
By a number of?
The number of protons exceeds the number of electrons.
By a number of?
By a number of 1.
Great. Okay, so because you need to know that basics. Sometimes when you lose those fundamental things, you know that the number of proton and number of electron in a neutral atom is always equal. The number of proton and the number of electron in the neutral atom is always equal. So if you change the number of electrons, because you cannot start tampering with the number of protons, it is saved in the nucleus. And it is the electron that is available, and it is the electron that is interacting with the outside world. So it is the electron you can maneuver or change. So if in this neutral atom, there are 11 electrons and 11 protons, that is like plus 11 minus 11. That means the sodium will not carry any charge. But if the sodium has given off one charge, it means I have plus 11 minus 10. If it has given one electron, it means you have plus 11 minus 10, which is plus 1. And that is why it is carrying plus. You know, you don't put 1. We usually don't write 1 when you are associating with something. Just like you don't say 1x. You just say x. You know that that is 1. So this is why, take magnesium, for example. Magnesium is plus, or neutral magnesium is plus 12. That is 12 proton minus 12 electron, plus 12 minus 12 is 0. That is why neutral magnesium is not carrying any charge. But when magnesium now decides to give off 2 electrons, it is left with 10 electrons. That means plus 12 minus 10. It means that the magnesium will carry plus 2 charge. It has an excess of proton with respect to the electron. And that is how you indicate the charges on a charged atom. So coming back to where we are going, you can see that all these elements, or the atoms of this element, can satisfy the octet rule by doing the same thing, giving off electron in the outermost shell. Because for this one to satisfy the octet rule, conversely, it will need 7. There's no way it can get the energy of that 7 from that reacting environment. The same thing, magnesium cannot get 6 from that environment, and aluminum cannot, honestly, get 5 more. So they will prefer to lose those electrons and become charged atoms, and whose electronic configuration follows the octet rule. So ionization energy, the concept of ionization energy, you've also learned in FSC 112, the amount of energy necessary to remove the highest energy electron for an isolated neutral atom that is in a gaseous state. Ionization energy are always positive because energy must be added to remove the electron. For you to remove an electron, you need to apply energy. So energy is being added. So the ionization energy for removing electron from an atom is positive. Note that for the metals, it is easier to remove the electron, the outermost electron. That means their ionization energy is low. If you remember your trend from periodic property, ionization energy increases from left to right of the periodic table, is it not? And it means that it decreases from top to bottom of the periodic table. So metals are usually on the left-hand side of the periodic table. So that means metals have more or less low ionization energy, and non-metals have high ionization energy. So, and that is why it is difficult to remove electrons from non-metals like oxygen, fluorine, chlorine, because you need a substantial amount of energy to remove any electron from those atoms. Therefore, in order for you to still achieve the octet rule, you just add rather than removing. Conversely, to gain an electron, elements at the end of the periodic table, especially group 6 and 7, gains electron to form negatively charged ion. Okay, most of these elements are non-metal, especially at the top of the group 6 and 7 of the periodic table. It is not all of them. In those groups that are non-metal, you find that as you move down towards the end of those groups, the elements gradually transform to metallic form. But at the top end, they are mostly non-metal. And these are elements with more electron in the atmosphere and are reluctant to lose this electron. Rather than lose the electron, they are capable of attracting electron that is given off by their partner that want to form bonding with them. For example, sulfur has 6 electrons in its atmosphere. Chlorine has 7 electrons in its atmosphere. Therefore, this element has 2 choices. It's either they give off these electrons or they attract. It is easier for them to attract electrons than to give off the 6 or 7 electrons. And when they do so, it means that sulfur will need 2 more electrons to form the stable octet of 8, and chlorine needs just 1 to form this. And you can see that sulfur is 2 minus. The same principle applies. Initially, sulfur has 16 proton and 16 electron. But on interaction with its environment and it's able to get 2 electrons, it now has 16 plus 16 minus 20. Plus 16 minus 20 will give you minus 2. And that's why sulfur is minus 2, carrying minus 2. Chlorine has 17 plus 17 minus 17 initially. Chlorine we have no charge. But if it's able to attract that 1 electron to become this, it becomes plus 17, plus 17 minus 18. That gives you minus 1. And that's why it's having minus 1. So at the end of the day, these 2 elements, like any other non-metal on the periodic table, are able to attract electrons, and they now form negatively charged ion. And everybody is happy because the driving force of those atoms is to have a completely filled octet so that they behave like noble gases and behave as if they are content. So the concept of, or the idea of attracting electron by an atom is called electron affinity. And it is the energy released that occurs when an electron is added to a neutral atom in the gaseous state or isolated atom in the gaseous state. Electron affinities are generally negative, okay? Because when you add electron, energy is usually released. Okay, energy is usually released. So know the difference now. If you are removing an electron, to remove an electron, you have to add energy. Okay? It's just like you wanting to take something from somebody. If you want to take somebody, it's whatever you want to take from the person, even if it's money, you want to take, whether forcefully or by wile or by fraud, you must use something. You apply an effort, whether it's by force or you use gun, or you trick the person, or you use your Yahoo Yahoo mentality. You must think. You must apply something to extract. But it's different from somebody. It's different from somebody willingly attracting the electron. Now, the two scenarios are that one, you are applying electron, but the other one, as you are adding electron, energy is released. So you have low EAs for metal, high EAs for non-metals. Sharing of electron by atoms. Now, we've looked at the two extreme ends of the periodic table. There are two extreme ends of the periodic table. So sharing of electrons by atoms. Other elements across the periodic table, those in group 4 and 5, you know they are in between. They are caught between the devil and the red blue sea. They do not find it easy to lose electrons. And they are not finding it easy to attract electrons. So because they are in this situation, they can also come to some understanding to achieve that octet rule. Rather than giving and taking, you can now say, my friend, atom B, look, you don't want to give up your electron. I don't want to give up mine. Let us share. They come together, they now share in such a way that the electron that A has, B can access. The electron that B has, A can also access. So that at the end of the day, it looks as if when you had the electron of A and B together, you have 8. So A is okay. When you have electron of A and B together, B has 8. B is okay. So there is also the concept of sharing electron by atom in order to achieve that noble gas structure. A moment. Okay, here's a little technical itch. So this brings me to electrovalent and ionic bonding. That is the first type of bonding that we'll look at. An ionic or electrovalent bond is formed when metals or two react with non-metals in group 6 and 7. You can see that those are the extreme end of the periodic table. The group 1 and 2, which are basically metals, and group 6 and 7, which are basically non-metal. It means that for the group 1 and 2, they can easily give off the electron to become ions or charged particle. Then group 6 and 7, which will readily accept the electrons to become also charged particle. When the reaction occurs, electrons are transferred from the metal to the non-metal. We've been saying that the group 1 and 2, they give off the electron to form ion or charged particle. Now, the electron they give up is not, do not just disappear into thin air. They are giving up the electron with the realization that there is another atom in close proximity with them that will be willing to take that electron. Okay, so giving up electron is not just for fun. There must be something in close proximity that will be willing to take the electron. So the electron are transferred from the metal to the non-metal until the outer electron shell of the resulting ion are identical to the noble gases. For example, look at sodium and chlorine. Sodium has one electron that it's willing to give up. Chlorine is needing one electron that it is willing to accept. So the sodium gives us its electron and is left with 8 electrons in its atmosphere. The chlorine readily accepts the 1 electron, and it also has 8 electrons now. So this one is now positively charged. This one is negatively charged. The two will now come together. They are attracted. You are very familiar with the law of attraction, that opposite charges attract and similar charges repel. Because they are opposite charges, by electrostatic attraction, they attract one another, and the resulting union is a compound of sodium chloride. So the compound is formed between two oppositely charged ions as a result of the transfer of electron from the metal, in this case, to the non-metal. The attraction is driven by what we call electrostatic attraction between the charges, the oppositely charged relative to the number of electrons that the non-metal need. If like we have in calcium chloride, calcium is giving up 2 electrons, but in forming a compound with chlorine, one chlorine atom can only accommodate 1 electron. That means you have to have 2 chlorine atoms to sufficiently take away the 2 electrons that the calcium is giving up. Again, there's an attraction between them because you have 2 positively charged and cumulative 2 negative charges by the 2 atoms of chlorine. Again, electrostatic attraction, and a bond is formed. A little bit of the energetic of this reaction. Ionization energy, removal of an electron from sodium, is positively it is an Hello? I don't know what's messing up. So removing an electron from sodium to form a positive ion is a positive energy exchange. Adding electron to chlorine is a negative energy exchange. One is endothermic, one is exothermic. And attraction between the two that is formed, the sodium and the chlorine in this case, we give an overall energy of formation that is negative. Right, it's not changing. So ionic compound is said to have been formed when you have electrovalent bonding between two ions. As the name connotes, they are formed by ions that has been joined together by electrostatic attraction. So ionic compound do not contain discrete molecule. What do you mean by discrete molecule? For example, in gases, if you have hydrogen gas or chlorine gas, these exist as discrete molecule that are different, that are separate from one another. Hydrogen H2, hydrogen H2, hydrogen, they exist like that together to form the body of gas that is the hydrogen gas. But for ionic compound, it is not discrete. It is joined together as an array of positive and negative ions. Okay, it's an array of positive and negative ions. Just like when you have your crystals, you have it directional. So it's a continuous joining of positive and negative ions that are participating in the bonding. The number of electrons lost by metal atoms equal the number gained by non-metal atoms, just like I explained a while ago. The electron do not just disappear. It must find a home in the non-metal. And the non-metal that is combining the metal must be able to accommodate the number of electrons that is being lost. At the end of the day, a neutral compound is formed. For example, when the sodium ion form with the or combine with the chloride ion, they form sodium chloride. The sodium chloride carries no charge because the positive here and the negative here are the same. They've been neutralized one another. So the compound that formed is a neutral compound. So other example of ionic compound you come across are numerous. Some as listed, magnesium chloride. So you can, in your spare time, go back to the slide, see how the sodium chloride and the calcium chloride was formed. Is formed in the slide, and you'll be able to walk back to see how magnesium and chlorine join together to form magnesium chloride. Properties of ionic compound. They are formed, as we said, by electrostatic attraction or Coulombic attraction between the positively charged and negatively charged ion. It is non-directional, that is, the strength of interaction between the two ions depends upon distance, but none on the direction. Ionic bond get broken when dissolved in polar solvent, like water. In other words, ionic compound are soluble in polar solvent. Polar solvent, just like water, okay? Then they have low ionization enthalpy. large lattice energy, high melting point and boiling point, good conductor of electricity when either in their molten state or in solution, they can conduct electricity because the ions can move about in solution and they are good conductor of electricity. Readily soluble in polar solvents such as water, but not that soluble in non-polar solvent. They form crystals which are hard and brittle. Hard and brittle. They're hard and they can break off at some point. So the slide also has tutorial question that you can look at the in your spare time, and that is it. That's the end of the class for today. If there are one or two questions, I can quickly take. If not, then we meet in the next class. Thank you.
So maybe I would like to take
because you want to ask questions, not because you want to.
yourself. Why? I can hear you.
Any question with respect to what we just discussed?
Yes, sir. Good morning, sir.
Good morning.
Yeah, my question relates to ionization energy.
Yeah.
You said when gaseous atoms, when they're about to lose their electrons, a particular energy is given off. So I want to understand, why do metals have low ionization energy and non-metals have high ionization energy?
Now, if let us first start from the trend of ionization energy. That as you move from left to right, okay? As you move from left to right of the periodic table, ionization energy increases. And from top to the bottom, it decreases. As you move from left to right, you are moving from metals to non-metal. But let us look at it this way. If, for example, I have lithium, okay? Lithium has 3 protons and 3 electrons. Intuitively, it means that every electron on lithium, okay, every electron that you have in lithium is being or is under the influence of 3 protons in the nucleus. Every electron in lithium is under the influence of 3 protons in the nucleus, which is attracting it. Then if you go to, say, chlorine, I mean, fluorine in the same, let's use the same period. Fluorine has 9 protons and 9 electrons. It means that every electron of fluorine is under the influence of 9 protons. So if I want to remove the electron of lithium, all I need to do is overcome the force of 3 protons. If I need to remove an electron from fluorine, I will need to overcome the force of 9 protons. Which of these two will I apply more energy?
The force of 9 proton.
The force of 9 protons. That's why the ionization energy for fluorine is higher, because you need a lot of force to overcome the influence of that 9 proton on that 1 electron that you want to remove from fluorine, unlike 3 that you want to. And that is why, as you know that as you move from left to right, the nuclear charge increases.
Yes.
Number of protons increases. That means the influence of the proton on any electron that you want to remove is increasing. Therefore, you need more and more energy. Just literally, you can say, for example, if you have a family that has been bequeathed the land, you have the sibling are just 3, and you have another family that has 9 siblings, and you want to buy the land from them. It is very difficult for you to buy from 9 people than for you to buy from 3 people. Because
Yes.
when they start calling among themselves, demand and everything, so just take it. I mean, transmute that to energy concept. I mean, that is the simplest I can explain it.
Okay. Thank you very much, sir.
Any other question?
Hello, sir. Can you hear me?
Yeah.
Good morning, sir. So, sequel to your explanation about arranging electrons according to their increasing energy level, which resonates so well with our principle. So, I wanted to confirm the difference between shells, subshells, and orbitals.
Hello, can you come in with your question?
I said I wanted to confirm the difference between shells, subshells, and orbitals.
Okay. Now, shell are basically like the same thing as orbitals. Shell is a common term that we use for it. For example, the first shell of an atom, which is n is equal to 1, is the first orbital of the atom. Now, there are some orbitals that are not just single or singularity. The first shell is single because it contains just the s orbital. Now, when you move to the second orbital or the second shell, there are 2 suborbitals there. In other words, it is telling you that the 8 electron that can be in the second shell does not have the same energy and the same spin. So for the second shell, you have S and P. That's why you have 2S, 2P. The S there can contain 2 electrons. The P can contain 6 electrons. Even the P also have degenerate orbital. You have PX, PY, PZ, which can also contain 2 electrons. So these suborbitals are like the fine print of an orbital. They are just like the addition of the suborbital will give you the orbital, the total number of electrons in the orbital. So in the second shell, you have 2 suborbitals. In the third shell or third orbital, you have 3 suborbitals, and so on. You know, when you do your electron, the hierarchy of electronic configuration, you have 1s, 2s, 2p, 3s, 3p, 3s, 3p, 3d. So it means that in the third orbital, you have 3 suborbitals, the s, the p, and the d. In the second orbital or second shell, you have 2 suborbitals, 2p, s and p, okay, and so on. Is that clear enough? The one that asked the question has disappeared. Any other question? Our time is 5 spent.
Sir, a last question, sir.
You know, it's not you that will say last question, it's me that will say last question.
Sir.
All right.
Okay, I'm sorry, sir. So pertaining to the previous question, does that mean atoms have orbitals divided into suborbitals and the suborbitals divided into degenerate orbitals?
Yes. That's quite right. Atom has orbitals that also has suborbitals. And some of the suborbitals could be degenerate too. That is, it's just like dividing the suborbital into another division. But the S has no suborbital. P has degenerate orbital. D has degenerate orbital. Okay, so
yes, sir.
All this is just to show by quantum mechanism to show that electrons don't just stay in one position, even in the same orbital. The electron in the same orbital also have different energy. That they are not just clumped in one place. Even if they are in the same degenerate orbital, one is spinning this way, the other is spinning the other way. It means that no two electrons can have the same set of energy,
Value.
the same value. Okay, if they're not different by the orbitals they are, they'll be different by the suborbital they have. If they are in the same suborbital, they might be different in the degenerate orbital that they are. If they are not different in the degenerate, they could be different in the spin direction with the spin.
Wow. Thank you very much, sir.
All right, this is where we end the class. We see you on Friday. Fortunately or unfortunately, Wednesday is a public holiday. So we'll see you on Friday. Then make sure that you go through the tutorial question. It's very important that you do.
No. Now go for big cards.
Yeah, bye.
Now get used to like look. I don't know why she like
It's Victor or Guinea or Shuku, whatever. You are in trouble. I will fish you out and I will deal with you. I'm trying to look at the chat to see whether the question you have to answer. I say, oh, carbon, is it easier for them to gain or lose? It has 4 valence electrons. Carbon, just like if you stayed to the end of the class, just like what I just explained, carbon is in the middle. It's not easier for it to gain. It is not easier for it to lose. Therefore, carbon, we primarily go into sharing of electron. And that is, that concept of carbon sharing electron forms a distinct part of what we call chemistry, organic chemistry. It's the chemistry on its own, the chemistry of carbon, and how it shares electron with other atoms to form a whole lot of compounds by catenation. Okay. Any other question? Okay, we'll see you in the next class. Bye-bye.